Okay, let's work on some practice translation problems here. So let's suppose we have a QL identity language with the proper name O, one place predicates P and T, and two place predicates F and N, where we imagine that the domain of quantification is all people. O refers to Oscar, P expresses the property of liking pizza, T the property of being a toddler, and F expresses the friends with relation, and N the neighbors with relation. And let's translate each of these 6 statements into this QL identity language. Starting with the first statement here, there are at least 2 people that like pizza. This one's straightforward. There are at least 2 people that like pizza. We just capture that by saying there is an X and there is a Y, such that X likes pizza and Y likes pizza. And moreover, crucially, we have to add that X and Y are distinct. And that's what captures there are at least 2 people that like pizza. If we didn't have this final clause here, then our formula would just say there is an individual that likes pizza. It would just be a more wordy way of saying there is an XPX if we left this last conjunct off. And I'll just note that strictly speaking, there should be some parentheses inside here, something like here or here, but because these are just 3 things being conjoined, there's no risk of confusion. So as our formulas get a little bit unwieldy here with lots of conjuncts, we'll often just leave inner parentheses out when there's no possibility of confusion. Okay, moving on here to the next sentence. There are at least 3 toddlers that do not like pizza. So this time we want to capture this by saying, okay, there's an individual X, Y, and Z, such that each of them is a toddler that doesn't like pizza, and they're all distinct from each other. So we want to say there is an X, there is a Y, there is a Z, such that X is a toddler that doesn't like pizza, so TX and not PX. And Y is a toddler that doesn't like pizza, so TY and not PY. And Z is also a toddler that doesn't like pizza, TZ and not PZ. And finally, the last step is saying each of these 3 things, X, Y, and Z, are distinct from each other. So we need to add that X is distinct from Y and X is distinct from Z. So now we know that X is not the same as either Y or Z. We need to also make sure that we're saying that Y is distinct from X and Y is distinct from Z. We already have the statement that Y is distinct from X here. So we need to add just that Y is distinct from Z. And now we need to make sure that Z is distinct from X and distinct from Y. And we already have Z being distinct from X here and Z being distinct from Y here. So that covers all our bases. We have that each thing is distinct from the others. So now our full formula says that there are at least 3 toddlers that do not like pizza. Okay, moving on to the next sentence here. At most 2 people are friends with Oscar. Now, there are a couple ways to translate this. First thing to note is that this is completely compatible with there being 0 people that are friends with Oscar. At most 2 people are friends with Oscar is saying, either 0 or 1 or 2 people are friends with Oscar. It's not 3 or more people that are friends with Oscar. That's what this is saying, or that's certainly one way to paraphrase what this is saying. It's denying that there are at least 3 people who are friends with Oscar. So we could translate there are at least 3 people that are friends with Oscar, and then just treat this as the denial of that. So if we went that direction, we'd say, okay, here's how we say that there are at least 3 people that are friends with Oscar. There is a X, there is a Y, there is a Z, such that X is friends with Oscar, and Y is friends with Oscar, and Z is friends with Oscar, and these individuals are all distinct from each other. Now we have the claim that there are at least 3 individuals that are friends with Oscar. And if we simply deny that whole thing, then that's the same as saying at most 2 people are friends with Oscar, because we're saying, well, it isn't the case that there are 3 or more, so then it has to be 2 or less. Another way to treat statements like this one, at most blah, 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 at most 2 people are friends with Oscar, is to see them, in this case, for example, as saying, well, if you take any 3 individuals, X, Y, and Z, that are friends with Oscar, then actually one of those 3, X, Y, and Z, has to be identical to one of the others, because there can't really be 3. There's at most 2. So on the other way of translating this sentence, which is ultimately equivalent to this one here, is to say, for all X, for all Y, for all Z, if X is friends with Oscar and Y is friends with Oscar and Z is friends with Oscar, if all 3 are friends with Oscar, then actually they can't really be 3 after all. It has to be that either X is equal to Y, or X is equal to Z, or Y is equal to Z. And this is another way of saying that at most 2 people are friends with Oscar. Okay, now moving on to number 4, there are exactly 2 toddlers who are neighbors with Oscar. So I'll go through 2 different ways to translate this one, the second way being kind of the preferred way, at least for me, because it's more efficient. It gives you a shorter formula. The first way, you could see there are exactly 2 toddlers who are neighbors with Oscar as asserting there are at least 2 toddlers who are neighbors with Oscar, and there are at most 2 toddlers who are neighbors with Oscar. If you combine those 2 statements, then that's really the same thing as saying there are exactly 2. So if we went that route, we would start with there are at least 2 toddlers who are neighbors with Oscar. So there is an X and there is a Y, such that X is a toddler and is neighbors with Oscar, and Y is a toddler who is neighbors with Oscar, and X and Y are distinct. So that tells me that there are at least 2 toddlers who are neighbors with Oscar. And then I add that at most 2 toddlers are neighbors with Oscar. So to say that, I can write for all X, for all Y, for all Z. If X is a toddler that's neighbors with Oscar, and so is Y, and so is Z, then X is equal to Y, or Z, or Y is equal to Z. One of those 3 individuals is identical to another one. So now this says there are at least 2 toddlers that are neighbors with Oscar. This says there are at most 2 toddlers that are neighbors with Oscar. So if I conjoin those 2, so here I'm sticking a conjunction sign in between those 2 and surrounding by parentheses, that would say there are exactly 2 toddlers who are neighbors with Oscar. Now, as I mentioned, this is quite unwieldy as a formula, there is a more efficient way to translate "they're exactly two toddlers who are neighbors with Oscar." We start in the same way with "there are at least two toddlers who are neighbors with Oscar." So let's copy that. And this time, rather than adding this whole thing here, "at most two toddlers are neighbors with Oscar," we just say, well, okay, we've said there's an X and a Y that are each toddlers that are neighbors with Oscar. They're distinct from each other. And we say, pick anything from the domain Z. If Z is a toddler and is neighbors with Oscar, then Z would either have to be X or Z would either have to be Y. And that ensures that these two individuals, X and Y, are the only toddlers who are neighbors with Oscar, because pick anything Z in the domain, if it meets that condition too, a toddler that's neighbors with Oscar, then it just has to be X or it has to be Y. So this is it's still a bit of an unwieldy formula, of course, but it's a more efficient way of saying there are exactly two than this up here. Okay, next we have "everyone other than Oscar likes pizza." This one, there could perhaps be a little bit of dispute about exactly what this English statement is saying. On one way of translating it, you could see it as saying, for all X, if X is distinct from Oscar, so if you have someone that's not Oscar, then they like pizza. If you translate the English statement in this way, note that this formula here, for all X, if X is distinct from Oscar, then X likes pizza. This is completely compatible with Oscar liking pizza. Both of these things could be true. This just says, well, anyone who's not Oscar likes pizza. What about someone who is Oscar? Well, they might like pizza too. This formula doesn't rule that out. So you could, I think, legitimately hear this English statement as asserting this. It's just saying, well, we know everyone besides Oscar likes pizza. What about Oscar? I mean, maybe he likes pizza too. If you read the English statement that way, then this formula captures what it's saying. Arguably, you could also read this statement, though, as not just saying that all the non-Oscar individuals like pizza, but you could also read it as asserting, in addition, that Oscar himself does not like pizza. We'd have to decide which of those interpretations is right. We'd have to get into dispute about, well, what is this statement literally saying versus what it is sort of normally used to convey, but maybe doesn't, strictly speaking, assert. Without getting into that whole debate here, if we do want to capture the second way of interpreting this statement, we would say it's saying not just that anyone who isn't Oscar likes pizza, but it's also saying that Oscar himself doesn't like pizza. So this, I think, is also a legitimate translation of this English statement, or so I certainly wouldn't mark this wrong if you gave this as a translation of this, even though I think maybe I tend towards seeing this English statement as literally just asserting this. I don't think I would mark this wrong. This is okay too. Okay, finally we have statement 6 here. Only Oscar is friends with every toddler. Okay, now this asserts two things. First, it asserts that Oscar is friends with every toddler. So to capture that, we say for all X, if X is a toddler, then Oscar is friends with X. And the second thing this is asserting is that everyone who's not Oscar is not friends with every toddler. So we also need to say for all X, if X is distinct from Oscar, then it's not the case that X is friends with every toddler. So to say it's not the case that X is friends with every toddler, we need to say it's not the case that for all Y, if Y is a toddler, then X is friends with Y. So here we have any toddler Oscar is friends with. Oscar is friends with every toddler. Here we have anyone who isn't Oscar. Well, it's not true that they're friends with every toddler. Only Oscar is friends with every toddler asserts both of these things, so we can see it as the conjunction of those two formulas.